Hello, class. This is MO 869, Introduction to Autonomous Vehicles. Lecture 15, Introduction to Motion Planning. This is going to be the introduction to the third module, which is the motion planning. So far we covered perception module and then localization and mapping module. Now we are going to start the third module, the motion planning. So we looked at this autonomous vehicle software architecture at the beginning of the course, and so far we covered these two modules, perception and localization module, and then now we're going to focus on decision and planning. Like I said at the beginning of this semester, we are not going to cover the control in this class, and you should be able to find other classes that focuses more on the control part. Okay. So here's the outline. We're going to start with coordinates and frame, and then we'll introduce you to degrees of freedom, degrees of mobility, and then we're going to cover holonomicity, holonomic versus non-holonomic. We're going to discuss what this physically means, and then we're going to also cover kinematics, forward kinematics, inverse kinematics, and then finally motion planning architecture. So just to make sure everybody is on the same page, we're going to start with coordinates. Probably many of you are already familiar, but we would like to review some of these. So world frame, it's also sometimes called global coordinates or inertial coordinates. And the frame, this coordinate is fixed to the world, so it doesn't move around. Whereas we have another coordinates that's called robot frame or coordinates, and that moves around with a vehicle. So here's the inertial frame, and then here's the robot frame, and we can describe the position and orientation of the robot with respect to either inertial frame or robot frame. So, and this is the inertial frame this is the position and orientation with respect to the inertial frame. And here's the robot frame or body frame, or also called local coordinates. In this case, we can describe things with respect to the robot frame or body frame. So obviously, when we describe the position or orientation of the robot itself, it's not going to change. But if we want to describe in the environment, then and if you want to describe that with respect to the robot, then there will those will in motions as robot moves around. Okay, and what we but there's a transformation we need to consider between the robot and the world frame, and that is this rotation matrix. So let's say there is this angle theta, where this is the angle between x-axis of the robot versus x-axis of the inertial frame, and let's say that is theta. Then we can compute the rotation. We can come up with the rotation matrix as follows, and by using that matrix, we can convert we can transform the coordinate between the robot frame versus inertial frame. And in the case of pi over 2, which is 90 degree, then if you plug that number into here, then you will get this matrix. And if you plug that in, then you will get the transformation. You can do the transformation between the two coordinates. And this is describing that transformation. So in the case of theta equals to pi over 2, then this is the rotation matrix you get, and then you can plug in the inertial position and orientation vector eta, and then you can compute the resulting position and orientation of the robot with respect to the robot frame. Okay. And let's talk about finite frame. This is very useful frame, especially if we are dealing with autonomous vehicles, because at the end of the day, vehicles vehicles are driven in the very structured environment, which is the road infrastructure. And because of that, vehicles do follow the lanes. And if you think about which coordinate to use, when it comes to driving this lane road infrastructure, global frame may not be most convenient coordinate to use, right? So what people introduced or adopted was this finite frame. What this does is we are going to introduce this new frame coordinates that sort of like robot frame, but this is conversion between the global frame versus the road infrastructure frame. So you can think of this as that, and let's take a look. Okay, so the values we are interested in would be position, velocity, acceleration, and the arc length. It would be the arc length is the as the name of it says, it's actually the length with respect to the curvature, the line we are interested in. So, and this is the mathematical description of that arc length. And what finite frame defines is the tangent vector and principal normal vector and binormal vector. So this is in 3D space. So in that case, let's take a look at this example. Let's say we have this line within 3D space, and then we can draw a tangent vector and normal vector and binormal vector based on this line. And using these definitions, we can come up with this Frenet-Serret formulas, which relates how these three vectors change over time with respect to as a function of the vectors itself. Okay, and we can also compute the curvature and torsions as a function of these line along the line. Okay, so the Frenet frame is going to move along the line, and by using this frame, if we use this Frenet frame that moves along the lane, then it'll be very convenient to compute longitudinal and lateral position of the vehicle and obstacles on the road. So, and you will see how this is actually used in the next following homework. So hopefully that then you'll have some experience with that. Degrees of freedom, degrees of mobility are two definitions we need to be aware of. Degrees of freedom, DOF of a mechanical system is the number of independent parameters that define its configuration or state. Degrees of mobility is a number of DOF that can be directly accessed by the actuators. A robot in the plane has at most 3 DOM. Which is position and heading. And let's talk about holonomicity versus non-holonomic robots. Holonomic robots, a robot is holonomic when DOF equals to DOM. And a robot is non-holonomic when DOF is larger than degrees of mobility. So what that means is, so in this case, we have 3 degrees of freedom, right? X, Y, and theta. And degrees of mobility can have 3 DOM, up to 3 DOM, but can have lower than 3 degrees of mobility. And we'll see some examples in the following slides. So, and when DOM is smaller than DOF, then it's called non-holonomic. Okay. And what that means is if a robot is holonomic, then you can move your robot in any direction you want using your actuators at any time, okay? But if a robot is non-holonomic, then your motion is somewhat, your actuation is somewhat constrained, so that you may not be able to move to one of the direction, for example. And when DOM is larger than DOF, the robot has redundant actuation, okay? Here's an example. In the case of differential drive robot, there's two wheels under the robot, and as we discussed earlier, we have 3 degrees of freedom, x, y, and theta. But when we have differential robots, we can only have access to x and omega, okay? But we cannot directly access y, okay? So this is not accessible degrees of freedom using differential drive, because you cannot directly move that direction, okay? You need to rotate and then move to move towards that direction. But even so, if this is assuming this is a robot frame, you can never move that direction, okay? How about a vehicle? So think about it, okay? What about the vehicle? Vehicle has 4 wheels, right? And then we have steering. So that will give you 1 degrees of mobility. So think about it. We will have examples in the following slides and lectures, okay? So here's more examples with different 3-wheel configurations. Let's say we have omni-wheel, 3 omni-wheel robots. Then DOM would be equal to 3. And let's say we have differential with caster wheel. Then we have DOM equals to 2. In the case of omni-steer, so what that means is we have 2 omni wheels with 1 steer, then we can cover 3 DOM. And then if we have tricycle, 2 wheels with 1 steer, then we have 2 DOM. And if we have 2 wheels and 2 steer, then we have 3 DOM equals to 3. Okay. Let's move on to kinematics. So there's 2 kinematics we need to be aware of. One would be forward kinematics, and the other would be inverse kinematics. Forward kinematics is when given the control parameters and the time of the movement t, finding the pose reached by the robot would need a forward kinematics, okay? Inverse kinematics is given the final desired pose and find the control parameters to move the robot there. at a given time t, okay? So forward kinematics, control input is input, and resulting state would be the forward kinematics. And for inverse kinematics, the input given is the vehicle state at time t, and we want to be able to find the control input to get that, to achieve that state. But to do that, it's going to need, we need to inverse the motion model, right? This is inverse kinematics, okay? So this is an examples for kinematics. Differential equations describe robot motion. How does robot state change over time as a function of control inputs? Is the motion models, right? And in the case of differential drive, this is the differential equations. In the case of bicycle model, this is motion model, where the input would be longitudinal speed and yaw rate or rotational speed, okay? And in this case, the input is vehicle speed and then the steering angle would be the input to the model, to the system. But they are not the actual actuator input, and we'll talk more about that in the following slides. Okay. So these are inputs. Okay. Okay. Here's the actuator part. So actuators of differential drive would be left wheel speed and right wheel speed, and we can control this left wheel speed and right wheel speed using controllers. Actuator controllers, okay? And the motion model is as follows, and in the body frame, okay? And the forward velocity u is going to be the average two wheel speeds, and this is going to be the rotational velocity, which is the delta speed between the left and right wheel speed, okay? And for the kinematics in world frame would require the transformation matrix here. So if we need to eventually compute where the robot would be with respect to the world frame, then and of course the transformation matrix is going to be a function of theta, okay? And we plug in this this motion model from the differential equation, the motion model in body frame, plug that in, and this is what we get in the world frame. Okay, so this is it, and of course you need to plug these two back into this, and then you will get the final motion model with respect to the world frame as a function of differential wheel speeds. Okay, let's take a look at inverse kinematics. So we want to compute u, which the input, and to do that we need to inverse the transformation matrix, and this is what we get. And if we work out this equation, then this is the model we get. So if you have x, y, and theta, then we can compute u and omega. But there is a constraint, because this robot is non-holonomic. The motion must meet this constraint at all times. Okay. And then we derived by definition, we had this actuator model, which relates the wheel speed to the robot motion input, and then we can compute control wheel speed as a function of u, and if we plug these in, then let me tag that back. Where did this come from? Yeah, that was correct. Okay, so we have wheel speeds of left and right as a function of u and omega, and we can plug this in to get the final equation, which relates wheel speed as a function of x, y, and theta in global frame. But this doesn't necessarily meet this constraint, so we need to plug these equations in. Then that's the final equation that meets this constraint. Okay. So let's take a look at sort of an example to see how that model can be used. So let's say we want to reach this goal, which is this state yg, xg, yg, theta g. Ideally, if robot would be holonomic, we can design controller in this manner. So compute error, and then use a control gain to converge to the goal. But in the case of non-holonomic robot, this controller won't work because because we cannot directly control all three degrees of freedom. So we need to use this type of inverse kinematics to design the controller, okay? Or help designing the controller, okay? Right, motion planar architecture. Let's take a look at motion planning architecture. This is an example of illustration of how motion planning architecture can be formulated. So let's take a look at this. So looking from top to bottom, it starts with route planning, and then behavioral layer, which is sort of a high-level decision maker. And then we have motion planning, and then feedback control modules, okay? So in this motion planning module, we are going to mostly focus on these three parts. But this route planning problem is sometimes there's less technical challenges in this problem. For instance, you can think of navigation. You know, how navigators provide you with route planning. So that's less of a challenging problem. So many of the research focuses on these two modules. So I will just basically provide you with many examples to give you an idea of motion planning architecture. But there's no one unique architecture that everybody has to use, but there's still some freedom out there, especially depending on the type of robots, types of autonomous vehicles. Different levels of autonomous vehicles will require different types of architectures. So assuming level 4, level 5 autonomous vehicles, here's some examples. So we have perception module, and then we use some representation for motion strategy, motion planning module, and then that goes in as an input, and using those informations that we get from perception and localization, and then we can make decisions and plan motions. And this gives you more detailed description of the motion planning module. So it starts with motion route planning, and then motion prediction or scene prediction, and then decision making, and predictive planning and reactive planning. I will talk more about this later on, but predictive planning is based on the predictions of surrounding vehicles and environments. We want to make good, intelligent decision and plan motions in predictive way. But predictions are not always correct, and things uncertain things do happen. So we do need reactive planning to handle unexpected situations, or including obstacle avoidance, okay, collision avoidance. Motion architecture. Another example for motion planning architecture is shown. Again, we get sensor data acquisition, and then perception. And we can also have some more information, data from wireless communication. And then based on all of that information, we need to make a decision. And behavioral planning, local planning is included in this module. And then based on that planning, the control module and actuator make that happen. Okay. Another example showing motion planning module. Here's the reference to this. And here's the motion planning module. And after after determining the global route and task, we need to do a little more local decision and planning. We need intelligence for that, and behavioral reasoning, trajectory planning, and control are those three that needs to be determined. So you can see things are quite similar in a big picture, but people draw it differently, and these figures and descriptions and illustration is somewhat different, and you will see more of that in the following slides. So here this is a little more organized, a more recent reference. Here's inception layer, or you can think of perception, and then we have behavior decision making layer, or motion planning is included, and then there's control layer, and then operation layer. Okay. Here's the junior from Stanford. This one is a pretty old figure from I believe DARPA challenge or urban challenge. I'm not sure, but so this is relatively old information. But anyway, still you can see that this perception navigation modules, and then there's this path planner that plans the motion of the vehicle, ego vehicle, and then the steering and throttle brake is the control actuator controller that to execute, to actually make that plan happen. Okay. And in the perception module, there's a different localization and perception algorithms to compute the environment state and the ego vehicle state. And this another old figure from BOSS, CMU. BOSS is the name of the vehicle. Carnegie Mellon University. When CMU participated the DARPA challenge, BOSS was the name of the vehicle. This example is not very well organized, but you get the idea of how decision and mode selector or planner selector is used to handle different situations. This is this example is providing figure for Carlos from MIT. And you can see again mission planner, situation interpreter, and that's mainly the motion planning part. And then we have controller, and then localization and perception modules are illustrated. Another example, but the point is this. In summary, path planner and velocity planner are determined sequentially. And scenario-based mission planner or state machine are often used to handle a wide range of scenarios. Simple trajectory predictions, such as constant velocity, is often used for motion planner. And lack of input-output information in most architectures. So this makes us hard to reproduce or actually understand the details of how the architecture works, motion planning and algorithms work. Okay. And there are some considerations for designing decision planning algorithm architecture. For instance, should we use deep learning? Deep learning has been showing us really powerful, really good performance for perception domain. But should we use deep learning in the motion planning as well, or should we still stick to traditional logic or probability-based motion planner, or should we use both? We do need to think about these considerations, because this learning-based motion planning is actually pretty good, pretty hot topic right now. People are investigating into these areas, but the concern is deep learning models are difficult to tune, calibrate, or modify the algorithm, difficult to interpret, difficult to debug when compared to logic or model-based approaches. And deep learning also requires data to train, whether it's simulator or real data. But we need to provide data, and this can be a problem when it comes to learning-based motion planner. Okay. And another topic I want you to think about is lateral and longitudinal planning. In many cases, they are done sequentially. Sequential planning, meaning that we determine a path, lateral motion first, and then determine velocity afterwards. But can we do it together? Well, if we try to come up with optimal control scheme that solves both problems together, then the problem gets really large and complex and difficult to solve in real time. So usually it's done in sequential manner, but But is that, best we can do? We might want to think about that as well. But as of now, sequential planning is the way to go, because of its convenience and computational load. Okay. So this is it for today, and I will continue with the motion planner in the coming Wednesday lecture. Okay. All right. Thanks for your attention, and I'll see you on Wednesday. Bye bye.